This is part 8 in a series of videos in which I am reproducing this ADM3A main board. If you're not familiar with the ADM3A, it's a dumb terminal, and of course that makes it a very old design. It's very interesting, totally discrete. There are no microprocessors or keyboard controllers or anything like that on this board. It's all discrete logic. There is a large scale device on here of sorts, which is the UART, and of course there's a ROM chip, but all the rest of it is discrete TTL logic, and that makes it very interesting. So we've got as far as putting together the basic parts. We've got the basic power supply parts fitted. I've got all the IC sockets fitted. Someone did point out that I'd missed one down in this corner. No, I haven't missed it. This is just a spare location. I used to do this sort of thing back in the day as well, where when you spin a board like this in the 70s and 80s, it was very expensive in terms of tooling. It cost thousands of pounds in tooling to get a board, and if you wanted to make a minor change, it was thousands of pounds again to make the tooling change. So what we used to do is just include one or more locations where you could fit an IC socket, and what you would do then is if you made a mistake and you needed gates or make a change, then you'd put a socket in, fit a device that you needed the gates from, and then you'd run some jumper wires. It was just kind of a future proofing, or a way of making sure that if you did make a mistake in the development, then it didn't bring the whole thing to a standstill. So no, it's not missing, it just doesn't need fitting. While we're on the subject of feedback, thanks to everyone that's given me information on this. Even if it's something I don't agree with, it's still nice to get the comments, because it can send me down a different line of thought that I may not otherwise have taken. So it's always nice to get comments. And so while we're on the subject of feedback, I just want to underline that one of the main goals of my channel is to try to maintain the concept, the design, the ideas in vintage electronics. In my day job, then, I design cutting-edge systems, embedded systems, using FPGAs, microprocessors, microcontrollers. And while that's interesting, you can get a lot of results these days for very little money. I don't find it particularly interesting. You can't really delve into the inner workings like you can with something like this, which is why I enjoy doing things like this. And for a true electronics enthusiast, I think this sort of project is very good. It's big enough to be significant. You can really get stuck into it, but it's discrete enough so that you can look into all the circuits in detail. There's no kind of black box, so to speak, that you can't see the inner workings of. And to put this into some context, and in line with some of the comments of maybe easy ways of doing this, I'm not really looking for an easy way of doing this. I'm looking for the most accurate way of doing this. There may be some compromises I have to make, such as the ROM, and sometimes it's a judgment call whether I should have sort of held out and try and find the mask ROMs, or bite the bullet and say it's not really feasible to try and do that. So in this particular case, we'll go with a more modern EEPROM. And to really put this into perspective, about 8 or 9 years ago, I was actually asked to design a dumb terminal for, I designed technology for other companies, and I was asked to design a dumb terminal. And obviously I wouldn't design it like this these days. It was based around something like this. This is just a demo board, but it was around this type of device. And so the entire dumb terminal fitted into one of these devices. In fact, it only used about 20% of the resources in this single device. It's an FPGA, and that one device replaced all of this, and there was enough in there for cores for several microprocessors and other things in the system as well. So we've really moved on a long way in the 40 or 50 years since this was designed. The difference really from an electronics enthusiast point of view is, other than the design point, you cannot really delve into the inner workings of this. You can debug it and whatever using software, but from the electronic side there's not much you can do other than plug it in and switch it on. That's pretty much it. Okay, so that said, what I'm aiming for, and this applies to all my projects, is to try to keep as true as I can to the original devices that I'm trying to duplicate. Okay, so back onto this project. How we go about building this from this point on. If you do decide to build one of these, you don't need to go to anything like this amount of trouble. It's just that this is the first time it's been built, so I need to test each block of electronics fairly carefully. And of course, this whole thing requires a clock to run, so that's the best place for us to proceed. So we'll be moving on to this part of the schematic and building up the clock circuit. Now the clock circuit on this board is, out of necessity, quite complex. There is a number of clocks, different clock phases, 2 master clocks, and obviously the need to feed these clocks around the board and them getting to the right place is fairly critical to the operation. The whole thing obviously needs to be timed properly. But the first thing is to get this clock actually running, and in some ways that's one of the most difficult parts of this build, and I'll explain why this is. This is something that quite often trips people up, and I see it a lot in old electronics, and people struggle to build these things. And it's not because they're making mistakes, it's because the devices they're using aren't the ones that were on the original schematic. On the original board that I had, it's actually not wired up like this. This is one of the few changes between the board I had, the original board, and the one that I put together here. So if you look at the schematic on here, it's giving part number of 74LS04. That's actually this device over here, and it's just a ring oscillator that's controlled by a crystal. And on the board that I have, the original board, it's a 74H04. Now you might not think that makes much difference, and quite often it doesn't, but in something like an oscillator it makes a huge difference, because the way that these devices work means that the switching characteristics, delays, and the levels at which they switch is different. So a lot of in terms of the digital inputs and outputs, yes, they are equivalent, but if you get it a circuit something like this, then they do behave very differently. So in the original board, this 270 ohm resistor is not there. It's not just not fitted, there isn't a place for it on the board. And I could have duplicated that and left this out, but what I've done is I've actually gone with this board layout, simply because if you don't want the 270 ohm resistor, you can just leave it out, and that's these resistors here. So there's one here, which are the two 1K resistors, and then there's the one that sits alongside the top resistor is the 270 ohm. Whether you fit them all or not depends on the device that you decide to go with, and it's up to you to determine how to get this running. In theory, if we go with this layout, it should run, and that's what I'm going to start with. I'm going to fit these components, and of course this is the same as this component, so we're going to fit this block of components and see if we can get the clock running. If we can get the clock running, then we'll move on to the dividers, and then ultimately we'll go on to the baud rate generator as well. This is just a series of dividers to give us the required clock rates for different baud rates, and then there's just a switch to select the different rates. Okay, but we'll start with the clock. I'll go away, get these fitted, we'll come back and we'll see if we can get the board up and running. Okay, so I've got the components fitted. This is not the final crystal I'll be using. I'm still waiting for the right ones to come in. This is a 10.92 megahertz crystal. It's the only one I had knocking around. It should be 10.88, but as I say, I'll change it once the proper one comes in. It's taking a very long time to get deliveries at the moment, but we'll end up with a clock of 10.92 megahertz if this is working. As I said, there are various options you have for this oscillator circuit. I'm using a 74LS04, and so I have fitted the 270 ohm resistor. If you're using the H or S type device, then you probably don't need the 270 ohm resistor, or it might need to be something a bit bigger. but really it's a case of trying it, or just stick to the LS version and use this circuit. That's on the assumption, of course, that it's going to work. I see no reason why it shouldn't. This is not the circuit I would normally use, but it appears like it should work fine. Before we plug the IC in, just want to quickly show how I clean the flux off the back of the board. I'm sure everyone's got their own favourite ways of doing this, and there is no right or wrong way of doing this really. It's just down to personal preference. I'll just drop the camera down so you can see a bit closer. Okay, I won't go to all the effort of setting this up under the microscope. I'm sure it's something you've all done hundreds of times anyway. But all I use is a bit of IPA, a small brush, fairly stiff, plastic bristles of course, not metal, and then just work it into the flux. The flux will lift fairly easily, you don't need to go mad. I'm not really scrubbing very hard, I'm just working it around the individual pads, and I'm not trying to get the flux off at this point, I'm just trying to soften it. And after a few seconds, just get a bit of kitchen towel or something similar, and you should be able to just lift off the flux, and you'll see it on the kitchen towel. And what I do is I just keep repeating this until the kitchen towel stops turning yellow. It doesn't take very long, it's usually 2 or 3 passes is more than adequate. And then right at the end, what I will do once I've done the entire board is I will give it a final rinse with IPA, and then just rinse the whole thing under a tap and dry it to get rid of any stains or any marks that are left on the board. And what you'll see is as you do this, the tissue will get lighter and lighter each time you go through, and then ultimately once the board's dried it will be very clean. All the residue and the remaining flux will have disappeared. If it's looking like this and all blotchy and messy, then it just means you need to go over it a few more times, and as I say, eventually you'll find that it will come up spotlessly clean. And this is what I do with repairs as well, so if I'm replacing components, I'll do the same thing just to make sure that the board looks clean. Most of the time the flux won't do any damage. The only exceptions are if you're using an acid-based flux, which will eventually cause or fairly quickly cause the board to corrode. So you can see that the flux is still coming up. And there will be quite a lot of it on a new board like this, simply because there's so many solder connections. But 20 minutes, rinse it off, and you'll end up with a spotlessly clean board. It won't do any damage to the board. Watch out for any components that might be susceptible to damage through IPA contact, but in general you'll end up with what is a very clean board. It's still a little bit dirty, but as I say, I'll go over the entire board when I've finished. But that's how I do it. You end up with a board that looks like it's been professionally cleaned. All the flux around the pins will completely disappear, and it makes quite a nice finishing touch to anything that you're working on or anything that you're building. Okay, so now we've got that done, I'll move the camera back up, get the scope in, we'll fit the IC to the board and see if this actually starts to work. Okay, so I've got the bench power supply hooked up to the board, I've got the scope set up, and what we'll do now is fit the IC. So it's a 74LS04, so that's 74LS04, fit it into the board, and this is landmark moment, our first IC into the board. That's in theory the entire clock circuit set up, so what we'll do now is power the board up, and we'll check pin 1 and see if we're getting anything here. So this should be the output from this oscillator, and then we'll check pin 4 to make sure that the buffer's working. I can't see why it wouldn't, but as I say, what I'm doing here is checking all the interconnections, and while you wouldn't normally do this, you'd obviously assume that all the tracks are correct. I can't make the assumption that any tracks are correct, so I need to check every node on the schematic. So I'll get it powered up. Obviously we're going to get more current than we had before. If you recall, we previously had 10 milliamps. I'll power up the bench supply. Okay, and it's now settled down to 21 milliamps. We'll try probing the IC. As I say, we'll start with pin 1 and we should be getting, if it's working, a signal somewhere close to 10.92 megahertz. So fingers crossed, let's see what we're getting. 10.92 megahertz, which is very promising. We'll move to pin 4 and again 10.92 megahertz. So that's looking promising so far. We're getting the clock running, it's running at the right frequency, it's full scale, so we're getting good drive, there's no issues, it's symmetrical, which is quite important. It is important that, that it's, although I'm not showing as a direct square wave here because there is ringing, I'm just using a floating lead here, so it's going to show some noise on there. If you want to get a true idea of how the signal looks, then we'll need to fit the ground clip. I will do that, I'll do it off camera because once I've got the clip on here I can't easily show you what I'm doing, my hand would be in the way. But it's also symmetrical in terms of duty cycles, so we're getting a nice looking clock signal, and I'm sure it will look quite square once we've got the ground lead on there. In fact, I will do that so you can see what I'm talking about, otherwise I'm saying something and not really demonstrating what it is I'm saying. Okay, so I'll fit a ground lead to the scope probe. I'll clip that to the ground connection. And then I'll scope pin 1 again. So now you can see it's a proper square wave, or at least much nearer to a proper square wave than it was. This is because we've taken out the big loop that we had in there without the ground strap attached. But you can see it's quite a nice strong signal. It's a good square wave. We'll go to pin 4 again, and that's looking fine. Again, bit of ringing, but that's more than likely still the probe, and it is looking quite a good signal. So now we've got the clock running up to this point, the next thing I want to do is put the clock dividers in. Just turn the supply off. So there are various clocks generated on this board. They're all derived from this master clock, but they go through, and some are gated clocks. So the first thing I want to do is to fit this IC, so this is used at least at this point as a gate for the clock. In this instance it's normally always enabled, but for whatever reason, maybe testing, they allowed you to disable the gate feeding the clock. Obviously we're going to need it here, and then what we'll do is we'll fit this binary counter that is used to divide the clock and feed various clock phases to different parts of the board. So I'll get this fitted first, and we'll make sure that we're getting the clock signal coming out of it. Now, if you're interested, this is a 74LS125 and it's position C15, which is the one next to the clock generator chip. Okay, we're ready to fit the next IC, C15. It's a 74LS125, but we also need to fit this resistor. These are effectively being used as gateable buffers, and this resistor is required to enable this buffer. It's permanently enabled in normal operation. I think this was just to allow the clock to be disabled so it could be fed with an external signal for presumably test purposes. But we need it to run, so I'll fit this resistor. It's actually part of a SIL package, so I've fitted that. That's, I don't know if you can see it, there's a black SIL package down here, and that resistor is one of the resistors in that package. So I've fitted that. Next thing is we'll get the IC plugged in. I would say here I've got some rubber feet attached to the bottom of this board just to stop it sliding around the bench while I'm working on it. You don't need to do that, this is just because I'll be doing quite a lot of handling of this board. Okay, we've got the IC plugged in and we're now ready to power it back up, and we'll be looking for a signal on pin 11 that matches the clock frequency, which is, if you recall, 10.92 megahertz. So I'll get the scope on there before I power up. pin 11, and now turn on the bench supply, and we can see we have our clock at 10.92 megahertz, and the bench supply is now showing 30 milliamps. That's obviously going up each time we fit a new IC. I just need to keep an eye on it to make sure it doesn't suddenly spike if we fit anything indicating there could be some contention somewhere. Okay, so that's looking promising so far. Turn the supply back off. So it takes a while to die down. That's mainly because we have this huge capacitor, and there's not many devices drawing current yet. Okay, so we now have a clock getting this far, and the next thing is to fit this device, C14, which is the next one down, and that is a 74LS161, which is a binary counter. We don't need to fit any other components at this point, just the IC itself, so I'll go and grab one of those, we'll get it plugged in and see if it works. Okay, so I have a 74LS161. One thing I'd say at this point is if you do buy components off eBay, anywhere else, and they're advertised as untested or new old stock, I strongly recommend that you buy one of the cheap IC testers and make sure they're working before you fit them to the board, otherwise you could spend a very long time tracking down faults caused by faulty ICs. It's not totally unheard of for sellers to knowingly sell components that don't work, or even they just can't test them and they don't work, but they're sold anyway. I always test all the ICs I get before I put them into my storage bins, so I know this works, but as I say, it's always worth testing them before you fit them. So we'll fit this into position. Also on the board, the silk screen actually tells you what each IC should be. So you can see here on the board it says LS161, so it does make it very easy to get them in the right place. So we'll get that plugged in. We'll get the scope probe, and what we'll do here is look for the clock output. It's found to various places on here, but one other thing to note is this binary counter will start up in a bit of an unknown state at the moment because we don't have a clear signal going to it. And in fact, if the clear signal is not in the right state, then it might not produce any output at all, so we might need to temporarily tie this high, but normally it should just run without doing that. So we'll start by checking pin 11. Okay, we'll power up the board, and as we can see we're getting a divided signal. It's much lower frequency now, 1.56 megahertz, which is what we would expect. I'll move on to pin 13. Sorry, pin 12, pin 13, and as you can see we're getting a proper sequence from a binary counter, so we know that this IC is also working, all plumbed in properly. So now we know that this top block on here is working, we're getting the correct clocks being generated, and really what we have here is the distribution, the clock distribution counter for the entire board. So what I'll do in the next few videos is go through all the major assemblies that are required for counting, etc. So the next one we'll look at in the next video is the baud rate generator, and then in the video after that we'll look at the character position counter, and by the time we've gone through all the blocks, then of course we should have a working board. If we find anything along the way that isn't working, then we'll stop, try and figure out what's wrong with it, and make any corrections that we need to. Okay, that's it for this video. As ever, if you want more detail on this, let me know, but it's looking promising so far. No errors found as of yet, and hopefully it will continue this way, but I somehow doubt we'll be that lucky right through to the end, but fingers crossed there won't be too many errors on the board.